Good. So thanks everybody for joining. And today we will present some new software that we're working on in Earth Science Analytics. As usual, we'll be talking about machine learning software, but this time we'll be introducing some new data types. And we'll also be introducing a new partner for Earth Science Analytics. And as Sarah said, also an opportunity to collaborate with us on an R&D project. And as you might have guessed from the invitation, the new data types is cuttings data. So we see here, upper left, a sample of cuttings from a warehouse. And there are these warehouses all around the world full of rock samples retrieved from wells. And in Norway, there has been basically an unprecedented digitalization project. It's still ongoing, the so-called Release Wells initiative, organized by Norway, and with the initiative from Lundin, and I saw Halvor Jare join the call. That's the key part in kicking that off, which means that there will be available huge amounts of information from these samples. And there are multiple data types created from these samples. And a key one is, of course, the image of the sample that we see here in figure number 3. So with this huge repository of digital data, of course, the next step naturally is to interpret the data. And after that, to make use of the data to create value. So we'll be showing today the machine learning and other software that we have built and are still building to interpret this data and to propagate this information up towards the bigger scales via well logs and also into seismic data, as illustrated to the right here. And we think that this is really a core thing to achieve, this bridging the gaps of scales, integrating the data from the very small scales all the way down to scanning electron microscope that we see down here to the left, and up to the regional scales of the analysis of entire basins and supporting the decision making that we make as geoscience practitioners. So some of you might be familiar with EarthNet, the main software offering from Earth Science Analytics, which basically covers well data analytics, structural seismic interpretation, and 3D property prediction, as well as large-scale data analytics. And today we will be discussing a new family of applications that we are launching, dealing with images. So it's basically computer vision applications. And we have been optimizing this computer vision technology specifically for cuttings data. But it's also useful for any other types of image data, be it traditional core images or microscope imagery. The industry collaboration we want to make sure you are aware of is between Earth Science Analytics and Rockwash Geodata. And Rockwash Geodata is a key contributor in digitizing the cuttings data, both independently on projects, multi-client projects, on projects with one-to-one with customers, and also they are part of this Released Wells initiative and the large-scale digitalization of the Norwegian cutting database, basically digitizing every sample from every well. And where we come in Earth Science Analytics is to provide the software, machine learning software, to interpret these images. But not only that, so we collaborate with Rockwash also for the domain expertise. So Rockwash has long experience in interpreting such images. So it's this coming together of the domain expertise, the software expertise, and the availability of the data that enables this the release of the untapped potential in this previously dormant data. So together with Rockwash, we are now inviting all the members of the Released Wells initiative to join an R&D consortium to build on top of what we have already created here in terms of software that we'll have a look at today, and take it further to maximize the extraction of value from this data set. So computer vision is a key part of this, since we have this enormous amounts of images. I think it's around 700,000 images. We know this technology from everyday life, simply by logging onto the phone in the morning. Remote sensing, robotics, all sorts of use cases of machine learning. And we don't have time to dive deep into the details of machine learning and deep learning. I'll just introduce two very superficial basic concepts here. That we have kind of two things we need to do. Number one is we need to train these algorithms, train a machine learning model. So to do so, we have training images, basically the raw images, and we have labels. So some representation of the ground truth of what is present in the images. That's the training set when we combine the images and the labels. And we need some machine learning algorithm. There's a lot of different ones out there. We pick one, we train it, and we achieve a trained machine learning model. With such a model, you can pass new images through it and retrieve the predictions. So very high level, and we'll definitely get into more details on what's going on behind the scenes in these machine learning algorithms in other webinars. Today we'll focus more on the data and how we can achieve what I call here multimodal image interpretation. So we'll train, or we have already trained models with multiple ontologies, basically classification schemes. You can classify rocks and images of rocks in many different ways. There are also multiple modes of machine learning algorithms, which we will get back to. And there is data that comes in addition to the images, what are called auxiliary data here. So it includes XRF, XRD, CamScan, SpecCam, and we can use data extracted from the well logs, stratigraphic information, and so on. So we'll train multiple models and make predictions with these multiple models to make sure that we provide a very rich interpretation of the data set. And the machine learning part is not the only part. In order to be successful at scale and in production with such technology, there are many other components that are needed. As I'm trying to visualize here with this wheel. And the reason for being a wheel is that because you need to go around the cycle multiple times. So at the base of everything, we need to make sure we have a data platform so we can contextualize the data to make sure that the data has relationship to the other types of data and can be used together. We need various data labeling technologies, which we'll show more. We need the ability to train the models, and we need the ability to do that efficiently. So we're offering no-code model training and model prediction software. Efficient app development, deployment pipelines, and then number 6 here, we need a means to track performance of the models and see where they do well and where they do not do well. And when we identify where they could do better, we need the ability to improve them, which basically means going one more lap around the wheel here. The need to go around and around also puts some demand on the efficiency of the workflows here. So you need to go around and around very fast. So these components here is basically what is needed for an end-to-end computer vision application. And we also need integrated workflows. So starting basically with a contextualization of the data, the images and the auxiliary data. Next, we label the data. We use computer vision and other machine learning techniques for rich, fast, and large-scale interpretation. And then we integrate the interpretation with well-log data. And in this step, this is the step where we can reveal any shortcomings of the models, any mistakes. So you need to iterate, basically, often meaning that you go back to step B here and relabel and go round and round until you reach the sufficient quality. And basically, in the end, you lift this and integrate it with the well data and the well data with the seismic data to ultimately support the business decision that we want to make, which can be in carbon storage use cases, in exploration use cases, in production use cases, field development, and basically anything where we need to understand the subsurface. So the no-code model training system that we'll introduce for the cuttings data is basically it's very similar to what we have for seismic data. This one is from our structural seismic interpretation module, where the user can select between a large number of deep learning architectures. These are fully configurable by the user. And it can be linked to any combination of training data to do the initial training of a model or to retrain a model that has been trained previously. So now introducing computer vision. So I'm sure you've all seen some of this online. It comes in multiple flavors or modes. Image classification being kind of the most basic one to the left here. So being able to say, tell if there is a cat or a boat or any other object in an image. So that simply tells you if the object is present in the image, or it can basically just be a tag of the image itself. In the second column here, we have object detection. So it tells you if an object is present, but it also tells you roughly where in the image the object is. So by drawing a bounding box around the object. And when we want more detail and precise localization of detected objects, we bring in semantic segmentation networks. So for these rock images, we will, that's what we want. We want to detail the detection and localization of the various fragments of rocks and minerals in the images. I'll go more into detail on the three methods to the right here in the following slides, which is unsupervised segmentation. We have a method that's using semi-supervised segmentation via semantic embedding. And then ultimately, we go to the supervised segmentation with the precise detection and localization of the rock fragments. So in order to achieve this, labeling is really the heart of supervised learning, I'll put there. So we need to make sure we obtain good training data for these models that we want to train. We need the ability to inject the expert knowledge in addition to information that comes from our auxiliary data. We need to be able to train multiple ontologies, basically multiple classification schemes. And we want to be able to use these multiple modes of computer vision. So on the bottom row, there's an example of image classification. We just such a model will just tell you if this image is a sandstone, is it a mudstone, limestone, a coal, or any other dominant lithology. But as you see from these images, especially the sandstone number 2 from the left, it's not only sandstone. The dominant lithology is sandstone, but you see there are some mud grains in the sample as well. So we want to be able to extract this granularity and not just slap a single label onto that image. So in order to do so, we introduce image segmentation, which basically draws these outlines of the fragments of rock in the image and produces a segmented image mask. We have already trained the image classification models with multiple ontologies on a dataset that is a multi-client dataset provided by Rockwash Geodata from the Barents Sea. And just have a bunch of images here to show how this classification works, starting in the shallow stratigraphy and going deeper. These are mudstones of the crater formation, Volmule mudstones, Collier mudstones, Knurr mudstones, Hackingen mudstones, the dark source rocks, Uglen mudstones, more mudstones in the Stør. And now we're getting to the sandstones of the Stør formation, sandstones of Nordmela, Tuboen, Bruholmen, Snadd. Now some mudstones in the Snadd formation, mudstones in the Kobbe formation, sandstone Kobbe, Klappnis, Havet, and so on. So you see from this selection of images that most of the time the images are not like pure single lithology, maybe except for the mudstones that very often are clean, there's only mud in them. But when we have sandstones, they are typically mixed sand grains, sand fragments, and mud, and also limestone. So to maximize the kind of information extraction from the images, we need to resort to the segmentation techniques. So for image segmentation, it's kind of straightforward in theory. You just have the raw image. You have a bunch of raw images, a bunch of segmentation masks that match the raw image. You train the segmentation model. Once you have the segmentation model, you push new images out and you predict segmentation masks. So the problem really comes into the production of the segmentation masks, the labeling effort. Just drawing these segmentation masks with a digital brush is very time consuming and prone to error. So what we have come up with here is basically a shortcut to this labeling task that leverages unsupervised segmentation and a technique called semantic embedding to produce these masks. I'll go a bit more into detail on how we do that. So when the user wants to do this, you basically select the images you want to work with, and you select an unsupervised segmentation model, which has been previously trained. And these unsupervised models, we could say that they are trained to create a bunch of classes where there is maximum similarity within a class and maximum difference between the classes. And they also want to maintain some kind of spatial continuity and produce a pixel a mask for the image. And in the next slide here is such a mask. So these colors here that just represent some class indexes that do not yet carry any geological meaning. And so clearly we need one more step. So we need to translate this segmentation index mask into what we call a semantic segmentation mask that contains the geological meaning. So that's when we need the semantic embedding. So we get the legend up here for the indexes, and we basically assign each index color to the appropriate lithology or mineralogy class. And when that is done, almost done, we get an image like this. So, indexes that have not been assigned yet remain white, and those that have been assigned get the appropriate lithology color in this case. And we can basically stop the manual work here and train on this and just leave out the white parts with the technical loss masking. But if we want to take it towards perfection, you can, of course, use a digital brush to fill in the remaining parts here and go to a completely infilled segmentation mask. And with transparency looking like this, with the limestone in blue, the quartz sand grains in yellow, and mudstone in the green. The green isn't that easy to see on top of the black there, but that's the mudstone. So that's the process of producing those segmentation masks. And in the last step, then we, of course, input them into traditional supervised image segmentation networks, train those models, make predictions that would result in segmentation masks for the entire data set. And the next step is obviously quality control. We have all these predictions. We need to check where they are good, where they are not good, and we need to make sure that we can improve them where they need improvement. So we have multiple techniques to detect these errors. We have the usual ones like the confusion matrix. So you can see where the prediction matches the label and not. And we have the ability to integrate this data with the auxiliary data, such as the XRF, XRD, the stratigraphic data, and so on. And then we can identify the candidate mistakes, send them back to the labeler to now have a more targeted approach to fixing the errors, run the process again, and iteratively improve the predictions. And we don't do this only once with one ontology. We basically do it with multiple ontologies. We do it with a segmentation technique. We do it with a classification technique. And we also use the object detection technique. And all these techniques and ontologies together also creates a data set that allows you also to use it for quality controlling and improving each of the models through a process that we call programmatic labeling. But once you have iterated enough and you're happy with the results, of course, the next step is to make sure you can propagate this insight across the scales. So from classification models, of course, you can just plot the classes according to their depth in the well and produce something similar to a well log. From the segmentation method, of course, we can compute the fraction of each lithology or mineralogy per area of the image and basically produce multiple logs from each of the images. And integrate those logs with the wireline logs and basically propagate it all the way up to the seismic scale, as we've illustrated here. So you see these in the middle there. We have we have a lithology log that you can produce in this way. You can compare it with lithology logs that are produced via petrophysics, and through attacking it from the petrophysics side and from the image recognition side, improve the quality of those logs. And those logs then become, in the final step, become the input to the 3D property prediction models that we run in Earth AI Seismic, where you can produce lithology volumes based on the seismic surveys, for example. And I'll just close on this. We are very dedicated on the cuttings problem at the moment. But I think you can see that the underlying technology here is very diverse and useful for all sorts of use cases. So we'll be using it. So we have also done some tests on microscopy, SEM images for nano fossils. We can use it for the regular core images. We've used it for documents, extracting information from document images, for quantifying macrofauna from imagery, and we'll be using it also for mapping the seabed for the purpose of both deep sea mining, ecological surveys, and also installation and maintenance of offshore wind farms. So that's the slides I had for today, and if you find this interesting, you're welcome to contact us on this email or directly, and we'd definitely like to hear from you and to see if we can find a collaboration to build on what we have done so far and take it further into the next steps.